Okay, today I want to finish off the standard, the 3.4 chemistry standard. So I just wanted to go over how we can use the delta H VAP and the delta H fusion for some of those intermolecular forces questions, because they can come up in that aspect as well. And then we want to deal with calorimetry, and then that's it for this. Then it's all done. So here's an example where they use delta H VAP, that's a vaporization, to talk about the intermolecular forces. So you may get it as a thermochemical question where you might have to write equations and do Hess's law and all that sort of thing, or you can get it to explain the intermolecular forces. So here you're given a delta H VAP for chloromethane being 22, and for methyl amine, or methanamine is the IUPAC name, is very similar, just slightly more, but you're also given molar masses. So if you're given molar masses, refer to them. They're there for a reason. Okay, so what type of intermolecular force depends on the molar mass? There's only one type of intermolecular force that depends on the molar mass. Hi, Thomas. So I can see you are typing. Right, the temporary dipole. Great. So you have to refer to them, so you have to work out what the intermolecular forces are, and remember, don't just say intermolecular forces. That's level 2 thinking. Now we've got to go in deeper. So you can't even get achieved if you just set intermolecular forces. So you have to identify the temporary dipole attractions, the permanent dipole attractions, and the hydrogen bonding. So here, both of these are polar, so they both have got temporary dipole forces of attraction as well as permanent dipole, and the amine can do hydrogen bond with other molecules because it's got a hydrogen attached to that electronegative nitrogen. So spell all that out. As I said, always imagine your teachers being really dumb and you've got to say every little thing. So your key points, you have to mention those different types of intermolecular forces and what affects them. So temporary dipole forces of attraction are affected by mass, number of electrons, and shape. So the shapes are pretty similar here. They're pretty much tetrahedral shapes. And you'd have to say, okay, the chloromethane's got a heavier mass, and so it'll have stronger intermolecular forces of attraction, stronger temporary dipole forces of attraction. I'm falling into that trap. And it's because of its greater mass, or its greater number of electrons, or its greater size. One of those things. Okay, then mention the fact that they're both a permanent dipole. Because you are not given the molecular dipole, you are not expected to say which one has a bigger molecular dipole. So you're not expected to say, oh, okay, I've got chloromethane and I've got an amine, and amine's more electronegative, so I would imagine the molecular dipole to be stronger. You don't have to do that, okay? Just say that there will be those. And then, of course, you've got to mention that this one has got hydrogen bonding. So really you have to say they're very similar in size, and that's because the amine has got the stronger hydrogen bonding, but the haloalkane has the stronger temporary dipole force of attraction because of its greater mass. So something along those lines. So you do need to compare and contrast in terms for excellence. If you just identified some of the intermolecular forces, then that would be achieved level. If you identified them and you said something about them, you could go to merit level. Okay, here's another one from last year, so get it more up to date. So you've got given a vaporization of sodium chloride and hydrogen chloride and the chloromethane again. So you can see we tend to use the same molecules again and again. So as long as you practice by going through past papers, you should be well prepped for the exam. And so you can see that it's much bigger for sodium chloride compared to the HCl and the chloromethane. So these are the sort of questions you're asked. Why is it so much higher for sodium chloride? Why is the vaporization for the chloromethane more than the HCl? And then a definition, which is a achieved grade. And then the other one is, why is the vaporization of NaCl bigger than the fusion for NaCl? Okay, so those are sort of questions, and I think the easiest thing for me to do is to actually go over, just get out the assessment schedule. Remember, you do know you can get the past exams and assessment schedules from NZQA. So you can say yes or no, or Y or N. Yep, okay, that's a very good resource. So basically you've got to say that it's ionic bonding. That's the key thing. So if you look over here, it's the ionic bonding that's stronger. Okay, and then for the fact that you've got to compare the HCl and the chloromethane, it's that same sort of thing. Temporary dipole forces of attraction are affected by mass. Your chloromethane has got a bigger mass than the HCl, and so on and so forth. So remember, you're given a periodic table, you can always work out the molar masses. Okay, so you'll notice here larger molar mass. Okay, and notice that they have spelt out temporary dipole forces of attraction. So for excellence, you need a detailed explanation. You've got to have pretty much everything in there that's over here. For merit, you don't have to have as much. This is a straightforward achieve level question. Remember, it's always 1 mole of a substance. So don't just say enthalpy of fusion is energy required to change a liquid to a gas. Or from a solid to a liquid, sorry, for fusion. That's too vague, because remember, the more particles you have, the more energy is going to be involved, so you must specify the amount. So it's 1 mole. And then the other one was, other question, remember, was about why is the fusion less than the vaporization? And that's because, remember, with melting, you break a lot of the intermolecular forces, or for NaCl, it's an ionic, so you break a lot of the ionic bonds, but you don't have to break every single one of them to melt. But when I want to boil and turn it into a gas, then I need to break just about every single bond. Okay, that holds the particles together. So for NaCl, it'll be, we've got to break pretty much every ionic bond. Is that clear on how to use the delta H vap, the delta H fusion, and so on in this type of example for intermolecular forces? Okay, so don't just pigeonhole it that, oh no, I'm only going to have it in as making equations or something. Okay, so let's, here I've started doing the answers. So let's focus on calorimetry now. Now, there are 2 types of calorimetry questions you could get. One is what we call the coffee cup calorimeter, and that is always done at constant pressure, because it's your air pressure that's hopefully constant, okay? And the other one is at constant volume. So it's a sealed container, so you can build up pressure inside, so your pressure is not necessarily constant, but your volume is constant. So this is what we call a bomb calorimeter. It's not because we're letting off bombs, although I suppose we could. It's where we do carry out a reaction, so for instance combusting it. That combustion reaction gives off heat, it gets absorbed by all the water and we measure the change in temperature of the water. So the more heat that gets given off, the more the calorimeter absorbs, okay, and therefore the higher the temperature. Coffee cup one is nearly exactly the same. It could be you're mixing two solutions together, or you could be burning a substance underneath and trying to work out how much of its energy is being absorbed, given off. And so we're trying to absorb the heat in the water, and we're checking how much the rise in temperature there has been in the water, or a decrease. So, can you see the mass of the water is important? If I have lots of water in the bomb calorimeter, can you see the temperature won't increase very much? But if I have a small bomb calorimeter with not very much water, can you see the same change in energy is going to make a big increase in the temperature? So as long as you get the idea from these pictures that the mass of the water or the amount of the water is important. Okay, so if you've got that fixed in your mind, the next thing you've got to fix in your mind is what's losing the energy and what's gaining the energy, because that's when you put a positive or a negative in. If I'm doing a combustion reaction, can you see that the reaction, if it's giving off energy, is losing energy? So what's gaining the energy is the calorimeter. So we work out first the energy involved in the calorimeter. So will the energy of the reaction be the same as that of the calorimeter, or will it be opposite? So say for instance I burn a certain substance here and I work out that my calorimeter has gained 300 kilojoules of energy. Can I say that my energy given, well, my energy here is also 300 kilojoules as a positive? Because I'm saying if this is gaining, it's become positive because it's increased in energy. And this one, is this one gaining or losing? It's lost. So that's why we say it's an exothermic reaction is negative, it's losing the energy. So you work out with a calorimeter, and if you come up with a positive value, then you know the reaction was negative. Or if you work out with a calorimeter and it's a negative value, then you know that the reaction has gained that energy, and so it's positive. Okay, so let's look at some calculations. First of all, you need to understand what specific heat capacity is, because you're going to be using that value always for water, and we'll always give it to you. So it's just simply a function of a material, of how much that material can absorb, how much energy that material can absorb to raise it by the temperature by 1 degree. So copper will have a particular specific heat capacity. It won't be very much, because you just heat copper a little bit and it gets hot. Any metal is like that. Water can absorb a lot of energy before it increases in temperature. So every material has its own specific heat capacity, and this sort of thing is just what you've got to learn. Okay, the definition. You do not have to learn any values. This will always be given. The units will always be given, and that's a good thing, because if you can't remember the equation, use the units to help you. So if I've got joules on the top, you know energy must be on the top. If I've got per gram, then you know mass must be below the line, or when you turn around, and the same thing with temperature. So this is my energy, and this is my specific heat capacity. There's the mass of water and the temperature change. So I know I said that should be below the line, but I've got to try and cancel out my things correctly. So if my 4.18 joules per gram per degree centigrade, if you imagine that unit there, what unit do I want on the left-hand side? It's sort of there. So I want kilojoules, okay? So in order to make sure that the per gram gets cancelled out over here, I must multiply by grams. In order for my per degree centigrade to get cancelled out, I must multiply by a temperature. Okay, so if you've forgotten, well, how does this formula work? Then just use that and go, okay, I need to cancel out the grams, I need to cancel out the degree centigrade. And then the dividing by 1,000, that's not that important. That's just to get into kilojoules. If you forgot the 1,000, then you're just measuring it in joules. That's all. That's the only reason why the 1,000 is there. So another equation, the way it could be given is Q for heat is equal to mc delta T. So m is the mass, C is the specific heat capacity, and delta T is the temperature change. Okay, and as I said, if your temperature change is positive, then your calorimeter is going to have a positive increase in energy, so this will be positive. And if my calorimeter increases and gets hotter, and so it has a positive energy, then remember the reaction has lost that energy. So remember, if you come up with a calorimeter that's in a positive, then the reaction's negative, or if the calorimeter was negative, then the reaction's going to be positive, because the energy's just been transferred. So here's a problem. I've got a solid that I dissolve in water, the temperature increases, I've got to work out what energy has been involved, and I've got to work out not just the energy, but the energy per mole. So I have to work it out per mole. Now we always have to tell you about the calorimeter specific heat capacity, so we're just saying the calorimeter doesn't absorb much, and so we're going to use the specific heat capacity, and you're always given that value. So I've highlighted now the key points. Always start these sort of things by listing your values. Okay, so the energy is what we're looking for. Okay, what is the delta H of the solution? What else are we given? We're given a delta T. The temperature is increasing from 23 to 34. So we're doing, you always do final subtract first. So the higher temperature, because that was the end temperature, comes first, and you subtract the initial temperature. So that's our temperature change. The mass of the water. Now there's some debate about whether you should include the mass of the solid with that. The way I gather with NZQA is you just use the mass of the water. You don't add the two together. When you go to uni and you have the more, here we make so many assumptions, so we keep it very simple. So for NCA, just keep it to 100 grams of water, because that's doing the absorbing. Okay, so don't add that value on. Right, you are always given the specific heat capacity, and I've just realized I have made an error there. That should be joules, not liters. I don't know what I did wrong there. We do need the mass of the potassium hydroxide though, because we have to work out the per mole. So how do we work out moles? It's always mass divided by molar mass. Now I wasn't given molar mass, but you can always work out the molar mass because you're always given a temperature. Always given a periodic table. So please remember that. So if you go, oh, I don't know what to do next, it may be because you're missing a molar mass. And so we want to finally work that out, and it's kilojoules per mole, which is different to the heat given off, which is just kilojoules. So we just substitute into the equation. So the mass of the water was 100, 4.18, the temperature change is 11.7. Check that your units have cancelled, leaving you just with joules. So my answer is in joules. We want it in kilojoules per mole, so we need to change it to kilojoules. Okay, and if my calorimeter has gone up positive by this amount, then my reaction must have lost by that amount. Okay, so where do we want to now convert for the reaction? We have to also work out the kilojoules given off per mole, so we need to know how many moles we've got. 5.03 divided by 56.1 gives you that many moles, and then you just simply divide it. And please always give your answer to 3 significant figures and the correct unit. Any questions with that? So if you've forgotten the equation, use the units and you can work it out. The units here at the end would also help you in kilojoules per mole. You know you've got to do the next step. You can't just leave it there because your units are kilojoule. Right, so here's from 2009 paper again. So this is the coffee cup calorimeter sort of style, okay, not the bomb calorimeter. And it's the same sort of thing in terms of the same sort of calculation. Now, what I've done here is a lot of students, they just go and if they do manage to list something, is this a useful list? No, because I haven't put units down or anything. I don't know what mass is relating to the water or what mass is relating to the substance. So this is pretty useless. You need to always give a context, and that's important because I know a lot of students just write a mass of numbers and it doesn't help them because they get lost and then they do the wrong thing, the silly mistake, and it doesn't help the teacher that in case you've made a silly mistake, if it's just a mass of numbers, they don't know how you're thinking and they're not going to sit there and try and work it out. They're just going to say, okay, mistake, wrong, you know, and move on. Okay, so have it fully listed. Okay, so I suggest you highlight or underline as you go through to make sure you've picked up every value that's been given. I did notice one year they threw in an arbitrary value that had nothing to do with the whole thing. So be aware, it's the first time I've seen it, but sometimes they may give you a value that is not relevant to the question. They just threw it in. Okay, and if you've got your values down, you can also, especially if you're stuck and you don't know what to do, if you see mass and molar mass, I hope you're thinking of the n is equal to small m over big M. If you're seeing the specific heat capacity, I hope you're thinking of the calorimetry equation. So at least you can move on to the next step. Because often the students say the most difficult thing is, where do I start? What do I do? And once they know where to start, you just plug and chug and you can get the answer. So list the values with your units. That'll help you work out what your equations are. Use the units to help you work out the equation, and then you just simply substitute and get the answer. Okay, now here I just did it sort of all in one step. I do recommend that you do it in separate steps in the exam. So you first work out the number of moles, and then you know, and so on. So it's, if you make a silly error, then at least they can say, okay, you worked out the number of moles correctly, we can give you an achieved for that, or something like that. Okay, so here's from last year's paper, so it's exactly the same sort of thing. So here we're burning methanol, and we've got the same sort of thing. So you do the list. When you get given a molar mass, I hope you're thinking of the n is equal to small m over big M. If you see the this joules per gram per mole, I hope you think of the calorimetry equation. And now you just simply plug into it, okay, after you've done your list. Notice, by the way, with the list, I make the mass of the water different to the mass of the methanol. So be specific when you make your list. And again, check with units to make sure that you've got the right equation, and then you just put it in. Now notice I have actually done that step of working out my moles. If you just did in your calculator 2.56 divided by 32, your answer will, your calculator will give you a 0.08. Now you should, for excellence, always show your significant figures. So put it as to 3 significant figures, because the 2.56 and the 32.0 were to 3 significant figures. Are you all clear on how significant figures work? Yep, so when you're multiplying or dividing, your total number of significant figures for that answer is the least number of significant figures of what you've multiplied or divided. So here it's 3 and 3, so you give your answer to 3, not more or not less. And so when I do that equation, calculation, I come up with this that the calculator spits out, and I give it off to 3 significant figures. Now you could argue that my water was to 1 significant figure, and I do agree with that, but for NZQA it should always be to 3 significant figures. Okay, so they should have ideally have said 5.00 times 10 to the 2 grams to show the 3 significant figures. So I do agree that this was not good in the exam paper. Okay, carrying on for that same paper, you'll often get a merit level opportunity where they'll say, why was this value you calculated over here different to, whatever. So they said part A. So I've just given you part A over here, and you'll see it was minus 726, whereas you've calculated minus 347. So you have to say something like, well, heat was lost to the surroundings because it's not sort of insulated. It may have been incomplete combustion, so it may not have all gone to carbon dioxide and water. It may have gone to carbon or carbon monoxide, something like that. So if you just gave one statement without any linking, so if you just said there was heat loss to the surroundings, that's an achieved. Okay, if you linked it, so like the second one, can you see there's more linking, then that's a merit. This is not considered an excellence level question, so you wouldn't get excellence out of this. Okay, so very quickly, because we've got about 2 minutes left, here's an example where so we've done one where we dissolve a solid, we've done where we burn something, okay, like a coffee cup, and the third type is when we mix 2 solutions. And the trick here is when you mix 2 solutions, then you've got 2 volumes, and if you're adding them together, the volume is going to be the sum of the 2. So just remember that. That's the trick for this. So here again you highlight, underline all the different values, list them down. It's always a good thing because that just sort of triggers your mind what sort of equations to use and so on. Now notice I've got 25 mils mixed together with 25 mils. So notice I've got my M mixture being 50.0 grams. Okay, it's a 25.0 plus 25.0, and I've said assume the heat capacity of the aqueous ammonium chloride is that. So we're assuming, I hope you know, 1 milliliter of water is 1 gram. So we're assuming that everything is behaving like water. So it's, although they're solutions, it's going to be grams, 50 grams. So there has been an I have given you the mass of the mixture. Okay, so this one has been kind and they've given you the mass of the mixture. They may not, but so if you're not given a mass, just work out if you're adding the 2 liquids together, 1 milliliter of water is 1 gram. And you just work out the change in temperature. Oh, hang on, you were given a temperature rise, so it's positive. Once you've got all that, you can work out. Do you notice I don't use molar mass now? I've got N is equal to C times V because I've been given a concentration. So that's why it's good to list things. And they normally give the equation as well, but it's useful to get the mole ratio. So you need to be sure that it's 1-to-1 ratio. So it's if you're working out per mole. So now we're just going grams is equal to MC. Energy is equal to MC delta T. There's your mass of the solution. There's the C, the specific heat capacity. There's your change in temperature. So that's how many kilojoules of energy was given off. Notice I've converted from joules to kilojoules. And so I need, for the reaction, I've got to calculate this. So I've got to do it per mole. For the reaction as written, and I can't remember if they actually gave you the reaction or not. But basically I've got 1 mole over here. So we were given identical concentrations. So you could have picked ammonia or you could have picked the HCl. It wouldn't make any difference. That would have given you the amount of ammonium chloride, and so you just take the energy released divided by the number of moles, and you get then the kilojoules per mole. So any questions on calorimetry? These tend to be merit excellence sort of questions. Excellence, you're looking at, have you got the 3 significant figures and the units at the end? Merit is the sort of plug and chug, and then achieved is if you got 1 part correct, like you worked out the number of moles or something like that. Or you've got the idea, but you may have made an error. Okay.